This is homework 3 for transport 1. First, we have 2 tanks with some liquid level. We have flows into tank 1, and that is Q1. We have a flow between tank 1 and tank 2, which is Q12. And then we have a flow out of tank 2, which is Q2. This flow enters tank 1 with a cross-sectional area, we'll label that A1, which is equal to 1 meter squared. And the flow Q12 enters into tank 2 with a cross-sectional area that we'll call A2, which is equal to 1.5 meters squared. We have a height here. This is height 1 of our liquid that is in our tank. And we have a height here, which is H2, which is the height of the liquid in tank 2. So tank 1 and tank 2. For our problem, flow 1, which is the flow into the first tank, will be a number that is given and varies with time. For us, it is going to be, it'll start at 1 meter cubed per second, and it'll increase to 1.5 meters cubed per second for a total of 50 seconds. Q12, which is the flow between tank 1 and tank 2, is going to be equal to 0.5 and the square root of the fluid height in tank 1 minus the fluid height in tank 2. And then the exit from tank 2 flow to the environment is equal to Q2, which is 0.25, the square root of the height of this fluid, so H2. The initial height of this fluid, so H1 initial, is equal to 2.0 meters, and H2 initial is equal to 1.5 meters, which is this height here of the fluid. So now that we have all of this, what we will be doing is deriving the differential equations for the liquid heights in tank 1 and 2, and then solving the initial value problem that results from that using Google Colab. We'll also then plot our results from 0 to 100 seconds. If this is at a constant state, then we know that our flow rate going into tank 1 is going to equal our flow rate going out of tank 1 and going into tank 2. So our change in volume with respect to time is going to be equal to the change in area 1 with respect to the height 1 over our with respect to time. And that is going to be equal to the flow rate going in to tank 1 minus the flow rate exiting tank 1 and going to tank 2. And we know that our area, our cross-sectional area, is constant, so we can go ahead and divide our area over, and what we get is our change in height of our liquid in tank 1 with respect to time is equal to the flow into tank 1 minus the flow out of tank 1 and into tank 2 over that cross-sectional area. And we'll do the same thing with tank 2. So our change in volume for tank 2 with respect to time is equal to the change in the cross-sectional area of tank 2 and the height of the fluid in tank 2 with respect to time is equal to the flow going into the tank minus the flow exiting the tank. And we can divide our area over again, and what we end up with is the change in our fluid height with respect to time is equal to the flow rate going in minus the flow exiting tank 2, which goes to the environment, over the cross-sectional area of tank 2. The reason we can divide these areas over and take them out of the change with respect to time is because these areas are constant and do not change with time. These equations that we have found, we will use in the second part of our problem, which is using Google Colab to then solve the initial value problem. So we know that from the problem statement that we have an initial value problem. So we need to import a way to solve that. So we're going to use from SciPy dot integrate import solve IVP. We're going to need arrays, so we're going to do import numpy as MP. We need to interpolate the data, so from SciPy interpolate import and we're going to also be graphing our data, so we need to import plot or from plotly dot subplots import make subplots. All right. This should be a 1. All right. And now what we're going to do is use those values that we solved for the change in volumes for both our tanks to write an equation. So our change in height with respect to time is going to use T for time and Y, which is our dependent variable. We'll define Y later as an array with various points in it for the heights. So we're going to say the height of tank 1 is going to be equal to the first point in the array, and the height in tank 2 is going to be equal to the second point in the array, or the element. So the 0 element and the first element. We need to do Q, our flow from 1 to 2 is going to be equal to an alpha value. We know that alpha value, it was given to us, but it could change depending upon the problem. So the alpha value times MP dot SQRT for square root, and we're going to take the square root of H1 minus H2. And then our flow from tank 2 to the environment is equal to another alpha value, alpha 2, times the square root of the height of the liquid in tank 2. Our change in height for the height of the liquid in tank 1 is equal to Qn, the flow that's going in. We're going to do that with respect to time because our time will be changing and our flow rate will be changing, minus the flow between 1 and 2, and all of that is divided by the cross-sectional area of A1. And nope, A1. Okay, there we go. And we're going to do the same thing with the second change in height for tank 2. It is going to be Q, the flow between 1 and 2, minus the flow from tank 2 to the environment divided by the area of 2. And we want to return the values of the change in heights, so DH1 and DH2, which are the change in heights for the tanks, or And now we're going to define some values. So alpha 1 is equal to 0.5. Alpha 2 is equal to 0.25. We need our cross-sectional area 1, which is equal to 1, and our cross-sectional area 2, which is equal to 1.5 meters squared. Our ending time is equal to 100 seconds. And we need the initial heights of the tank. So initial heights we'll call h underscore I, and we're going to make that an array. So tank 1 is initially 2. Oh, my number lock is on. There we go. All right, 2, and the second tank is 1.5 meters. We need the values for our flow. So the Qn value is going to be equal to an array, and it's going to be 1, 1.5, and 1.5. And we need the time values that correspond to that. So Qnt is going to be equal to 0, because that's our starting time. 50 seconds, because that is when it changes from 1 to 1.5 for the flow rate. And our Tn time, which is equal to 100. So we can go ahead and put those in and test some of the values out. So let's do hi. We're going to do the first element, and that should give us 2, and it does. Let's go ahead and delete that and do our flow in values. We're going to do the 0 element. That should give us 1. All right, and then if we change this to 1, because Google Colab does its iteration starting at 0, so now this should give us 1.5, and it does. So go ahead and delete these, and we can continue on to the next part. So now we need to interpolate our flows. So interp 1D, and we're going to do our time values for the flow is the first part, because that's our x value. Our y values are our q values, so qv, and then the kind is going to be equal to previous, so that's going to mean it's going to look at the previous values for the interpolation. Okay, and so our result is going to be equal to we need to solve the IVP for our change in height with respect to time, so dH dt, and we're going to do from 0 to t end for our time. We need to do our initial height values, so h underscore I. Our method is going to be equal to redo, and so that we can see all the values, we're going to do dense output is equal to true. We want our heights at a lot of different values so that we can plot them and not just the 3 values that we were provided here. So what we're going to do is do t is equal to np dot line space, which is going to make a list of numbers that are from, we're going to say from 0 to our end time, and we're going to want 100 values, and what it's going to do is go from 0 to our t end, which in our case is 100, and those values will be evenly spaced and that we'll get a total of 100 values. So now we can go ahead and type, we're gonna shift enter that, and result, it's gonna give us the y values and our t values. So here the array for the t values and the y values that correspond to those. So if you look through here, we want to solve it, and so what we need to do now is use the t that we did here for the evenly spaced out values of time from 0 to t end with 100 values, and we're going to do our solution is going to be equal to result.sol to solve it with, those should be parentheses, with our parameters being time, or lowercase t. So we can shift enter that, and what we should get are, let me delete this, hold on. Now shift enter. Okay, and now what we get is our heights for the two tanks. And you can see here that the first tank starts at 2, like we initially said, and the second tank starts at 1.5, like we initially defined up here for our initial heights of 2 and 1.5. And next, what we want to do, now that we have these values in our answer, we're going to want to plot these. So now we need to make our plot. So what we're going to do is figure equal to we're going to make a subplot. Rows is going to be equal to 1, and our columns is going to be equal to 1. And we need to add the points to our figure. So fig dot add scatter, these are going to add our points. So the first is our x value, which is going to be our times, so t. And then we need our y values, which is going to be equal to our solution here. It's going to be equal to the first array. So we need to do solution 0. And we can go ahead and name this, since these are our heights for the first tank, we can name it H1. All right, and shift enter that. That should make, I think this should be subplots. Oh. Okay. Did I spell columns wrong? No. Oh, it should be shortened to that. There we go. Okay, so there it is. Delete those. Now it should be good. And we should get a plot. And we do. So these are our first heights these are our heights for tank 1. So we're going to go ahead and do the same thing. So we're going to add to that figure using the scatter, and x is going to be equal to t, and then, which is the same as our last one, and y is going to be equal to the solution, but it is going to be, those should be, yeah, they should be brackets. It would be 1 instead of 0, and then we need to do, we're going to name this again. Name is going to be equal to H2, because these are our heights at tank 2. So we're going to shift enter that, and we get our heights for tank 2 as well. So looking at our graph now, we have our heights corresponding to times, and we have it going from our time of 0 to our time of t end, which we said was 100. We have the heights of tank 1 in blue, the heights of tank 2 in red. So we're going to update our figure in order to add some titles for our graph. So we're going to update the layout. Width. Actually, I shouldn't have to. If I can, I think I can just type x-axis. Title is going to be equal to time in seconds, and then the y-axis title is going to be equal to heights, and then we need a title for our graph, and that's going to be 2 tanks fluid heights with time. And that should give us those graphs. Oh, we should say the heights in meters. I think it's meters. Yeah. So now we have a title for our graph and axes labeled, and we have our H1 and H2 lines labeled as well. So yeah, that is homework 3.